All right, welcome everybody. This week we're going to continue our discussion of the Hugging Face Ultra Scale Playbook. Very long, soon to be book, very long blog post discussing how to train LLMs on multiple GPUs. So last week we started the conversation and we really got more into the details. So we're not going to have time today for anybody who's new. But basically, we covered some of the basics. One is that in neural network training, not specific to LLMs, but just in general, we have a forward pass and we have a backward pass. And when a model has multiple layers, just by the very nature of the most efficient way to do the back propagation, the gradient calculations, what happens is you start at the forward pass at your inputs, and you intuitively work your way to the outputs of the model. But the backward pass starts at the last layer where the outputs are, calculates the loss, and then calculates gradients backwards in the layers going from the last layer all the way to the input layer. And once you have the gradients, then whatever your optimizer is, if it's Atom or vanilla SGD, whatever, can decide how to calculate the updates to the weights based on those gradients. So if it were vanilla, SGD, it would just be a small constant learning, a small learning rate, scalar number times the gradient. But with momentum and with other things, the calculations in Atom are a little more complicated than that. So that's the very basic thing. And so everything's going to really be talking about how are we going to get the forward and the backward passes done using these various techniques that allow us to take advantage of multiple GPUs. So then the next concept, as we scroll down, is this idea of in an LLM, how big are these various things? So naively, I used to think the thing that requires the most GPU memory is going to be all your parameters. And it turns out for an LLM, that's practically the farthest thing from the truth. It might be the smallest of the main components. So there's a handful of components we're going to talk about. So there's the parameters, which in this diagram is showing several steps, 4 steps in some LLM training calculation that got profiled. So without going into the details, just to get the general gist, you can imagine that if you have, say, a 1 billion parameter LLM, they're going to take up an amount of memory that's equivalent to the height of this blue teal bar. And if you're using Atom, then Atom needs memory in order to calculate its momentum and variance that it uses for every update. And it actually needs to store 2 floating point numbers for every parameter. And so you'll see the pink is actually bigger than the blue. And almost everybody uses a variant of Atom. And so this pink is actually double the size of the blue typically. Then you have the activations, which are the results of the calculations in the forward pass. And these are needed in order to be able to calculate the gradients in the backwards pass. So these need to be stored. And in an LLM, what happens is we have not only a certain number of parameters, right, in the attention and the feed forward, but we're processing sequences. So maybe you have approximately 4,000 words and a sequence length of 4,000. And even though the weights at every token position, the weight for the first word and the weights for the second word and for the third word are all identical, and you don't need multiple copies in the GPU, the actual activations for every token position are unique. And so the activations grow linearly with the length of your input. And so this makes LLMs very different from things like a CNN that's doing, dogs versus cats classification. And so the activations get much, much bigger in an LLM than the parameters or the optimizer state. Exactly what this scale is, let's not worry about that now, but just know that this light purple color, which is the activations, they're much larger than either of those other 2 things. And then the final thing is the gradients themselves. They need to be calculated, and a certain amount of them will be kept around, and the optimizer will be applied in order to update our parameters in the blue. So that's the cycle, and these are the challenges we're going to have when it comes to fitting these LLMs on our GPUs. So um, want to move forward with the different techniques, but let me just pause here and just check to make sure if there's any basic questions before we move on.
Hey, Ted,
Yes, sir.
why is the width of the purple area in the first one, the activation, so much wider than the other? Do you know?
Yeah, so what the article says is that there's various places where PyTorch will allocate memory in the
Hmm.
very first step. And so it'll
Oh,
do a bunch of things that it never does later on. Hopefully, later on, it can just, assuming that you're going to have many, many more steps, thousands of times more steps, it can afford to spend a little longer in the first step figuring
got
things out in order to make all subsequent steps as efficient as possible. And so
okay.
I
So
think in
that's
some cases, it's actually hard coding memory addresses and doing things. Um, they note later in the article that we're not yet at the point where we're talking about having multiple GPUs and doing communication,
mhm.
but they say communication is way more expensive if you're trying to send, let's say, your attention parameters, right? And they're not in contiguous memory. So if you're trying to send a message to GPU number two and it's spread out over different things, that's way more costly than if you can have one contiguous block of memory and say, hey, I want you to send from 5,000 to 10,000. I want you to send all those bytes over to GPU number two. So I don't know the details. I have not, programmed GPUs, but the article talks about that.
Mhm.
There's a lot of work done to make sure that you get nice contiguous blocks of memory for things later on. And so you might not be worried about layer 17 right now, but in the first pass, it's worrying about all of those things and figuring out how to arrange them.
Okay, okay. That makes sense. Which I think we saw some of that with DeepSeek too, didn't we? That they were trying to be very efficient in terms of colocality and things like that.
Yeah, I don't remember how much we went into the first versus all subsequent steps, but
Yeah.
it makes sense that a little extra time spent planning, a little
Hmm.
so it's sort of allocating. And according to this diagram, you can see that its allocations only go up to here around 50, but there's a very, if you can see on your screen, a very skinny tall spike at the
Mm.
beginning of the forward pass where um, it actually uses even more than that. So not all of this is apparently, fully pre-allocated. And again, I don't know what settings were used to do this particular profiling, but the most important thing to understand is that with LLMs, we're going to have challenges with these activations growing very large. And the larger the sequence length you want to support, once was common, 4,000 was a reasonable sequence length. Now anything less than 16,000 seems kind of small. And if you're
Mhm.
going to support a million, then that means that, this purple area relative to something that's 4,000,
Mhm.
what is that? That's going to be 256 times bigger. So if this thing fit on one GPU, nominally, you would need a minimum of hundreds of GPUs just to fit all this stuff.
Okay.
Okay.
Thanks.
All right. So now that we have the basics, we got the forward pass, we got the four big components of memory: parameters, optimizer state, activations, and gradients. Okay. So last week we were able to start the conversation about data parallelism, and data parallelism is nice. It's relatively straightforward. Let me scroll a little bit more. Data parallelism, in the sense that what you can do is you can just have, if you have three GPUs, you can have three copies of your model, and you can run data through all of them in parallel. And at some point, they need to communicate with each other such that you get the overall gradient from all the data that was sent to all the GPUs, and then your optimizer can do an update. Okay. And naively, you might just do this where you say, let's do all the forward and backward passes and then do a bunch of communication. But what you can do is you can overlap this communication. So we're not going to cover all of that in the same detail today, but but that's the gist. And this is relatively simple to do in terms of code, and this is very simple to implement, and you can get a very good, close to linear speed up to a very large number of GPUs using nothing but data parallelism. The problem with simple data parallelism is that it actually doesn't solve any of our problems with fitting things on GPUs, because up to now we've just talked about naively, we fit the entire model onto GPU number one, and then we're going to put extra copies on all the other GPUs. So this isn't really getting to the whole, it's getting to parallelism, but it's not really getting to the problem most people have, which is they want to train a bigger model and it doesn't fit. And so now we need other strategies. So data parallelism is the first of the 5 parallelisms that are described in this article, right? The 5 Ps they talk about. But vanilla data parallelism is the one that actually doesn't help you fit things. Okay, it does allow you to train faster, because if you get a linear speed up and you're trying to process 1 trillion tokens, if you can do 100 GPUs data parallelism at once, you're actually going to finish 100 times faster. So it has value in that, but not for fitting. So what we need to talk about is we had some strategies here where you're seeing there's certain communication that's overlapped. Now we're going to say we can do more sophisticated data parallelism, and so we're going to start to talk about this thing that got named the zero redundancy optimizer. Okay, and so when you combine zero with data parallelism, what that means is, depending on the level, instead of having full copies of the model on every GPU, they can actually use a distributed algorithm which allows them to spread the data around between the GPUs and not actually have to have full copies of everything. Okay, so zero level 1 talks about the optimizer state itself. Okay, so simplistically, let's say you just have 2 GPUs. Okay, and in my very first layer, I've got I've got a particular weight matrices for, let's say, the attention, the Q, K, V, and whatnot, right? And then I've got weight matrices for the MLP part of the transformer, okay? In vanilla data parallelism, I'd have complete copies not only of the parameters of the weights, but also of all the information that Atom needs to calculate the gradient step each time. But you could imagine that if you were clever about things, then you could have one GPU do the update for the attention weights, and just send that information to the other GPU. And while it's doing that, the other GPU could calculate what all the updates should be to the weights for the MLPs and send that. And so they could split the calculations in half. And not only are they splitting the calculations, but the information they need to do those calculations is partitioned such that now they don't actually need to keep all the Atom information. They only need to keep the Atom information on the subset that they're calculating. I don't remember if we have a detailed diagram for this. Here we go. And so here, the optimizer state is this light purple, okay? And so what you'll see is here they show with dots, dot, 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 but you physically see 3 GPUs, the first, a middle one, and the last. And in the forward pass, we need our parameters, okay, in order to calculate the output of the model, right? And we're going to have all of our activations that we calculate based on this. And so nothing has changed so far, okay? But then when we get to the backward pass, what we're going to say is, oh, the first GPU, you calculate the update on a small set of the parameters over here. At the beginning, you calculate some in the middle, you calculate some at the end, and then once they do those calculations, they exchange them with each other. So these lines are the communications. Okay. Um, and then once they have all the information they need, um, then they do the optimization, and then they share that optimizer step with all the other GPUs because all the other GPUs have copies of the parameters and they need to update those. So there's two steps of communication, okay? One needed in order to calculate the optimizer step, and then one needed to broadcast, so to speak, that optimizer update to all the other GPUs that have a copy of the parameters. So that's what this animated diagram is trying to show us. And if you do this, then if you just look at all of these diagrams combined, what you can see is that all the other memories stay the same, but this light purple one, the optimizer state, that one gets split by a factor of n if you have n GPUs that you're doing this. I saw briefly there was a hand raised. Any questions about this? Is just zero level one.
Yeah, I'd raised the hand, Ted, just that I wasn't aware of the 0, 3. So 0, 1, and 2, each GPU still has the full model parameters.
As the full model parameters in 0, 1, it also has all of the activations
Right.
from its forward pass of the model. All right. Okay. So you can see here that there is a penalty that you will pay because basically when you do this communication, kind of everything stops, right? So if you have information you need in order to calculate the optimizer step on this first portion here, you really can't do anything productive until you get the communication from the other GPUs that have the info that you need. Okay. And so again, you get all the stuff from them, and then you're able to calculate your update. And you say, oh, this parameter we should lower it by 0.1. Fine. Then you need to tell all the other GPUs lower that parameter by 0.1. So 0, 1 does come at a little bit of a cost, but the good news is that the amount of information that they're transferring is or the frequency with which they're doing this is relatively small. And so 0, 1 is generally considered like pretty darn good. Next, we get to 0, 2. So if you think about this and you're like, okay, what do I need to have in order to calculate the optimizer update for a given parameter? I need the activations and I need whatever my optimizer state is. So if I'm only going to do calculations on a small set of updates, there's really no reason for me to have all the activations. I'm never going to use the other ones. I'm only going to use the activations for this little slice from my data and from all the other GPUs. So when we get to 0, 2, do we have as pretty of a diagram? I think we do. Now what you see is in this diagram over here, instead of having the full width of the pink stuff, okay, I really only need the activations. I'm sorry, I only need excuse me. This is the gradients. I misspoke. I only need to worry about the gradients associated with my particular slice that I'm doing the optimizations on. And I believe it says here somewhere, the communication cost for 0, 2 is very similar, almost identical to the cost of 0, 1. So basically, there's no reason to stop at 0, 1. If you're going to do 0 at all, you might as well do 0, 2. It's going to save you more memory per GPU at no extra communication costs. So this is like the easier part of 0. The harder part of 0 is when you get to 0, 3, which says, is there further we can go instead of just having the optimizer state and the gradients? Can I save even more? And the answer is yes. You can actually split up the parameters it's going to add to your communication, but you can split up the parameters as well. Um, and so this is going to require some passing things around. I don't know if there's like one really great diagram for 0 level 3. I guess this is the diagram we get, or the two diagrams we get. Um, uh, but basically what happens, my understanding of what happens in 0, 3 is to do the forward pass, you need, to do the forward pass for layer 17, you need all the parameters for layer 17. Okay. But no one said you had to keep them around when you're doing layer 18. All right. So what happens is there's communication where everybody who has one little slice of the parameters sort of broadcasts them, shares them with all the other GPUs, and we all calculate layer 17. Then we all throw away the other, if it's 10 GPUs, the other 9/10, we throw away those, and then we communicate all with each other so that we all have layer 18's parameters, and we do what we need to, and then I throw away 90% of them because I don't need them. I'm not in charge of keeping them. I'm only charged keeping 1/10 of them, and then we all calculate layer 19, and so on and so forth. So it's not the case that your total memory goes down to 1/10, because at some point you need a full layer for any one given layer, right? So in a, let's say, 30 layer model, your memories for these pieces are cut in 1/10, plus you need 1/30th sort of full memory, because at some point you're going to be working with a full layer and you might be like constructing things. So they have the equations in here, and so that's where there's sort of an extra penalty associated. But you can see that, especially as we talk about the big models people want to train, they're 30 to 60 layers. So the fact that you have to keep that you might at some point reconstruct one layer based on the messages from everybody else is not that big of a memory penalty if you're really talking about 1/30th or 1/60th of the model that you're sort of keeping in memory at one time.
But doesn't it mean effectively you're like reloading all your parameter weights every forward pass?
And backward pass, there's
Yeah,
communication as well.
yeah,
So you
yeah.
can do your optimizer step and everything. So for this reason, 0, 3 is not always recommended. Okay. 0, 3 saves you even more memory. And if that's the difference between it fitting in your memory or not, you're gonna do it. But if you are GPU rich, what we'll see when we get to the very end of the article is they don't recommend 0, 3 very often because of all of that extra communication and reconstruction. But in a pinch, if you say, I only have 8 GPUs and this model's yay big and I've done all of these things and it still doesn't fit, going from 0, 2 to 0, 3 will save you more memory.
But again, from those earlier diagrams, a really big chunk of your memory is dedicated to activations, right? So
Yes,
the
so
parameter
it will,
isn't the whole thing anymore in our
yes,
less naive model. Yeah.
yes. So it will turn out that um, 0, 3, or what I believe in PyTorch is called fully sharded data parallelism, FSDP. Okay. Um, FSDP is, uh, it turns out it's like the really easy thing you can do. You could basically have your model code and you don't have to modify, and you can tell PyTorch, turn on FSDP. I have 8 GPUs, and it'll partition your optimizer state, your gradients, and your parameters 8 ways, um, so that it's just 1/8, dramatically reducing that memory, and then it'll communicate the pieces that it needs automatically without you having to write any of the code to tell it to do that communication. You just turn on FSDP. Okay. So uh, uh, so the advantage of 03 FSDP, there's two advantages. One is it's the only one that is like the code-free parallelism that you get. Okay. So if you're really rich, if your model's small and fits in GPU, you can just do data parallelism without any of this zero business. But if you're trying to save some memory, uh, 0, 1, 2, 3 FSDP, these are the things that you potentially can turn on in your framework without having to write, without having to modify your model at all. Okay. But as you point out, unfortunately for LLMs, this doesn't solve the biggest problem because once you're training a large model with a long context, this is a tiny, tiny fraction. Okay. So these are the three smaller components of the four and the one that doesn't grow with context length. So when you're doing your million context length, you, you've reduced the size of the smallest contribution. Like yay, you cut the thing that was only 5% of your memory, by a factor of 8 or however many you want to cut it. So that's why we need to go on to these other parallelism techniques.
So, Ted, one thing I was thinking is that sharing, the communication would probably be done through NVLink, right?
So this is going to depend on your architecture, okay? So if you have one of these like 8H100 nodes, like they talk about in this article,
Mhm.
then it's NVLink and it's very fast and you don't incur much of a penalty by having this communication.
Yeah.
Once you go to 16 or higher way communication, then you start paying more of a penalty because you're not going over NVLink, you're going over like whatever. And then depending on like your data center architecture, right? Then you might see like, oh, once I go past 64, I'm now suddenly like whatever, you know what I mean? Like leaving a rack and going to the next rack. And so then now you see an even bigger penalty going from 64 to 128 than I did going from 32 to 64. But in this article, they constantly talk about the penalty going from 8 to 16 is really big, relative speaking, like you can do almost any technique you want up to 8 ways, and because the communication is so darn fast, uh, uh, you don't really pay too much of
Is
a penalty.
is NVLink architecturally limited to 8 nodes, or is it just typical?
Uh, Somebody else might be able to answer that
Okay.
question. My understanding is, you know, you can't just daisy chain these things and get whatever. So you can't just go to 16, go to 32, go to whatever.
Yeah.
Uh, and whether or not what exactly the limitation is, if it's power, if it's voltage, if it's latency, I don't know the gory details, but from what I understand, yeah, the way NVIDIA built it, you get 8, and that's the most you can have.
Okay.
There is no such thing as a 16-way node, to my knowledge. All right. So this diagram summarizes, and what you see is this is full data parallelism, full copies on every GPU, on 8 GPUs. Okay. And they show it for a couple different sequence lengths. And so you can see here, this orange really grows as we double sequence length. Okay. Well, actually, this is quadrupling. Um, uh, so for 0, 1, the blue and pink are the same size, but the purple's gotten smaller. For 0, 2, the pink and purple have gotten smaller, the blue's the same. And then finally, for 0, 3, for FSDP, both the blue, the pink, and the purple, all three of them have gotten smaller, but to your point, Roger, they were the smaller part to begin with. And this orange, for length 16,000 just ekes under their, 80 gigabyte uh, per GPU memory limit. As soon as you want longer context, which is very common these days, you cannot do it using just data parallelism. You will need other techniques. And what we'll see shortly is the downside is none of these other techniques are fully supported in the frameworks. So you can't just say, I want to download Llama 3, 70, 80 billion, and turn a flag that says turn all these parallelisms on. You need to actually modify your code.
Does it look like that first column that the optimizer states, that doesn't look like an atom optimizer state, right? Isn't that twice the parameter size? It's little, not to scale.
It does look like more than double, but they may have done something for this diagram where we haven't talked about it, but they said, oh, these parameters are 16-bit and the optimizer states are
32.
32-bit. So
Hmm.
actually now it's twice as many of them, but each one of them is
It's
twice as
twice as
big,
big.
so it's four
Okay.
times as big total.
Yep.
Yeah, they
I
don't
guess.
really in this. I love this article and the diagrams are really great, but they don't really explain what the settings are for any one diagram.
Yeah.
So sometimes, yeah, sometimes you have to kind of noodle over like, well, the proportions aren't the same in this diagram and in that
Right.
diagram.
Okay.
You have you have sharp eyes, Roger. All right. So that gets us to the end of data parallelism. Any questions about data parallelism 0123 FSDP? All right. So uh if you are doing a different kind of model that doesn't have really long sequence lengths, there's a decent chance that data parallelism and the support that's built into like PyTorch, that's all you're going to need. So if you say I have one GPU and it has 24 gigs, but my model is slightly bigger, um, uh, um, if you can get two 24 gig GPUs, then there's a decent chance that these techniques are going to be enough. The that FSDP will be enough to get you to be able to train your model. Um, but for LLMs, we're going to need something bigger. So the next concept we're going to talk about is tensor parallelism. So in data parallelism, if you imagine this multi-dimensional tensor that describes everything in our system. So one dimension is the batch size. Okay. One dimension is the size of our data itself. So like, the hidden dimension of your LLM, every token might get embedded as a length 8,000 vector, right? So the word the is 8,000 floats, and the word boy is a different 8,000 floats. We're going to have the sequence length. We're going to have other dimensions. So in data parallelism, what we're really playing with is the batch dimension. And so we were saying if you can do a batch size of 4 on one GPU and you can have 8 GPUs, you can essentially do 32 samples simultaneously. Okay. And then using FSDP, you can even save a little memory while you're doing that. In tensor parallelism, what we're going to do is we are going to split things based on the actual model dimension. So if the word boy is a vector of 8,000 floats and we use 8-way tensor parallelism, we're going to store 1,000 of those floats on GPU 1, the second 1,000 on GPU 2, and so on and so forth. And we're also going to take our weights and we're going to split those into 8 ways. Now, there are going to be, if you think about the math, there are going to be times when you do a matrix multiply and you need information from a different portion of this tensor, even if you're only responsible for the first 1,000 of the input and the first 1,000 of the output, you can't get the answer without also getting information from some of the others. So tensor parallelism is definitely going to require communication for this. So the article, they show some examples and they say, so here's an example of matrix multiplication of a 4x2 times a 2x2 matrix resulting in a 4x2. And then they show two ways in which you can split this. So one thing you can do is if you see this W matrix, which is 2x2, you can split it by its columns. So the first column is 1020 and the second column is 3040. And so down here they show 1020 and 3040. So if you have full copies of the data multiplied by this subset of the weights, you get two subsets of the answers that you can just stitch together column-wise. Okay? But there's another way that you could split it, okay? So remember, here's our weight matrix. Instead of splitting columns, we could split rows. So we have 1030 and 2040. So notice here we have 1030 and 2040 in the rows. If you do it this way, you now don't need two copies of your inputs. You can split your input based on the columns, and then you'll get two temporary outputs, which now you cannot stitch together. You have to sum together. And this is just based on the properties of matrix multiply, where if you're familiar with, you go row of the left thing times column of the right thing, row times the left thing times column of the left thing, and you're summing them up. And so basically you're either splitting out, you know, the row column multiplies so that you never have columns in common, and then you can just stitch them together. If you split up the rows, then you're going to have columns in common and you have to sum together. So there's two different ways you can do this, and basically, I have to always think about it, but basically the idea is that if you have two matrices that you're multiplying together, then you kind of like want the one on the left to be row wise and the one on the right to be column row and column wise, or vice versa, whatever. But you don't want them both to be row wise. You don't want them both to be column wise. Okay. And then that minimizes the amount of communication that you need to tell the other GPUs the thing that they don't have. If you look at some of their sample code, we didn't have sample code for data parallelism because you kind of get it for free. But now here, if you look at this, they say, here's our row parallel linear, multiplication routine. And this is, not the shortest of code. It's not the worst in the world or whatever. But this is breaking things up. And I think someday you could get support in PyTorch where it automatically does this. I don't think this is the hardest thing. But there's two things that you need to know. One is it is a bunch of work for PyTorch to be splitting apart your parameter, weight matrices into, row and column subsets and whatnot. And the other piece is right now, it's not smart enough to know which ones should be split row-wise and which ones should be split column-wise. I think that's the main reason today why you have to do it manually. It's because you have to actually decide, my attention Q matrix, how am I going to do it? My attention K matrix, do I do it the same way or do I do it differently? And like every single one. But then once you did that, theoretically, you could, if you had like a naming convention like Hugging Face does, right? You could say every matrix that has this regex in the name, that matches this regex, do it row-wise. And everyone that matches this regex, do it column-wise and blah, blah, blah. And then not manually do it, but have PyTorch just then follow that rule and split them all for you. I think something like that would work. I have not actually implemented this, so take it with a little bit of a grain of salt. So here they then go into a little bit of details and say, hey, for the transformer, this is the way that you would actually kind of want to break things up.
Sorry, may I ask a question about
Yeah,
the
please.
previous one? On the split up, how to do the like backward path? Does it need some special handling, or it just some standard library would handle it, or the standard algorithm?
I'm pretty sure things work pretty well for the backward pass, because basically to do the backward pass, what you need is you need to know, what operation was performed so that you know what the functional form of the partial derivative is, right? If it were x squared, it's 2x, right? And you need to know what the actual value is. So if x was 10, then 2x would be 20. So basically, if you're responsible for doing the forward pass and doing the calculation, as long as you store that activation, as long as you store the result of the operation, then the backward pass can flow through, in the same way. So the other property is, you notice, like, for example, I was showing um, uh, here we sum the two together. So one of the really great useful things about derivatives is they're linear operations. And so you can, whenever you just have things like addition, you can always split things up and calculate subparts of gradients, right? And you can sum them together and stuff.
Oh,
So
oh,
I
I see.
apologize. That was a little bit hand wavy, but but I don't remember if they go into great detail in the article talking about it.
Uh,
But I'm pretty sure what they say is that like yeah, you essentially the information you need for the forward pass is the same information you need for the backward pass. So if you've gathered that information for the forward pass, you're in good shape for doing your backward pass.
okay. I think I got it. So basically, it's just a standard sum operation, and then the standard way of doing gradient just work.
Yeah, so like if you look at let's do this diagram, it's even simpler. If you look at this diagram, you have two copies of the input matrix X. Okay. And so you do a regular matrix multiply to get this piece, and the other GPU does a regular matrix multiply to get this piece, and then they stitch them together. So on the backward pass, when you have the gradients associated with these 8 locations, you unstitch them. And so you send half the gradients here, and you send half the gradients there. And then you do the calculation, the chain rule calculation for this matrix multiply, separate from this. But because we had 2 copies of X, whatever 8 gradients we get now here, we have to sum them together in order to get the total gradient over here. So this
I see.
broadcast on the forward pass becomes a plus, a summation on the backward pass.
I see.
Does that make
Thank you.
sense? Yeah,
Yeah.
so there is a little bit of work to do, but there's nothing tricky. It's not like, oh shoot, GPU 1 wound up with this information, but GPU 2 needs that on the backward pass. Right?
Yeah.
I think that's the way things generally work out, is that what you use on the forward pass is what you need on the backward pass. So yeah, so I'm obviously skipping a few many of the details in this article. So feel free to reread sections or all of it. And so then they basically say, you can see here in the MLP for a transformer, they recommend that the first weight matrix, this is a Vaswani where you have 2 matrix multiplies. Um, uh, the first one you want to be column-wise, the second one you want to be row-wise, and this prevents you from having to exchange information between the different GPUs. So as long as you sort of do this analysis, um, uh, you can do this, and then I believe for the attention part, what they talk about is, oh, there's actually this really convenient thing for attention. We do multi-headed attention, and the heads never talk to each other. So you don't even need to exchange information to combine them, because the heads work independently until you finally gets to the weighted sum of the values. So as long as your tensor parallelism is equal or less than your uh, your multi-headed attention factor, then you're good. So if you have 16-way multi-headed attention, you can do 2, 4, 8, or 16-way tensor parallelism, and the attention part is really easy to split out. Right at the very beginning, the very end, there's communication, but in the middle, each attention head operates just completely independent. Okay. You are a little bit up the creek. I don't think the article says that there's a convenient way to do multi-headed attention if you want to go 32, but you only have 16 head attention. Maybe somebody's done it, but I think if I remember right, this article does not discuss how you want to do that. So yeah,
Ted?
there's not a great way to handle tensor parallelism past your number of heads. Yeah, Roger.
So in that scenario, would the KV cache be separate then and just maintained on each of the separate GPUs?
Yes, I believe so because it's the KV cache is per head. And
Yeah,
so there's really no
yeah,
cross GPU communication needed. You just keep
cool.
track of your path. So so yes. So this diagram tells you how should you handle the MLP portion. Should do this
Hmm.
person column, this portion row. But for the heads, as long as you're doing less than the number of heads you have, less than or equal to, uh, it's really kind of like very little work,
Hmm.
um, since the heads are already operating fully independently. Um, yeah, and so let's see here. I forget how they exactly transition here. Um, but so in a uh, they say that note that tensor parallelism is not a silver bullet for training. We've added several communication steps directly into the computation path of our model. Um, and this is the key thing to understand about tensor parallelism compared to basically all the other techniques that we are going to talk about, um, is that when you get to that communication portion, there's no way to overlap it with computation. You cannot hide it. Okay. So when we're talking about the data parallelism, we couldn't hide all of it, but we were able to hide portions of the communication and overlap them with the computation. For tensor parallelism, you don't really have that capability. And this is why tensor parallelism, when we see the final recipe, is sort of uh, uh, the least favorite technique to be used. It's not because this is that much communication, but for every amount of communication it is, your GPUs are sitting there doing absolutely nothing while that's happening. Uh, I don't know if there's some super clever technique you can do where, like, again, if you have if you're GPU rich, I think as the article talks about it, uh, and you don't have any trouble fitting things onto your GPUs, then I think there might be a trick where you can fit your GPU in half of the amount of memory that you have on your GPU. If you can do that, then basically during this communication portion, you can actually, with the other half of your GPU memory, be doing some other calculation where you're basically doing the meaty work part. And so you sort of have the two halves, and you can try to overlap that. That again is going to require some pretty hairy code. Um, uh, but vanilla tensor parallelism, I think, well, maybe we'll see at the end of this section. I think they do say on their systems it worked up to 8 because of those super fast NVLink uh, communication channels that you were talking about, Roger.
Yeah,
So they had nodes with 8 GPUs, and they could get it to work. But as soon as they went to 16, you'll see the communication penalty. Um, for 8, it was maybe like a whatever, a 7 point something times speed up, right? And as soon as you go to 16, it's like, nope, now it's only, now you have like 15% overhead. So now it's only 14 times as fast. You're not getting linear speed up from the GPUs anymore.
but Ted, you'd said tensor parallelism is typically applicable to the MLP, right? So is there, I think we get to the expert parallelism, where it's more of a share nothing type of, or share less
Mhm.
type of architecture. So that might be another reason that, in a sense, tensor parallelism competes with MOE parallelism, expert.
Uh, I wouldn't necessarily say competes. I would say tensor parallelism is made obsolete
Yeah, okay,
by
fair enough.
MOE.
Yeah,
Yes.
fair enough.
So You can do a form of parallelism. We're going to get to that's the fifth one, expert parallelism. You can do a form of parallelism that's cheaper than tensor parallelism if you have MOE MLP layers.
Yeah.
So we just saw the attention does tensor parallelism very well.
Yeah.
And if you now do expert parallelism instead of tensor parallelism on your MLPs, now you're doing really well. So yes, great point. Okay, so yeah, so here's the diagram that I was talking about that says how much of a penalty do you pay waiting for communication? So here's 2 GPUs, here's 4. They say it's like 10% penalty. So you'd like this to be twice as fast as 2 GPUs, but it's actually only whatever 1.8 times as fast. 8's not bad because now it's a 12% penalty, right? So, but then you can see when you go from 8 to 16, wham, all of a sudden now you're spending 40% of your time GPUs doing nothing. And if you go to 32, now it's almost 2/3 of the time it's doing nothing. Actually, I think these are actually cumulative. So this is 40% compared to the 8, which already has these other penalties. So, so tensor parallelism is a way to get your model to fit on more GPUs, and intuitively, it's relatively straightforward, right? It's not that complicated a concept to just say, I'm going to take my weights and I'm just going to cut them either vertically or horizontally, right? So I find it to be pretty intuitive, but you are paying this penalty. Again, I was mistaken until I read the article. I thought it was the volume of communication that killed tensor parallelism, but it's not exactly just the volume. It's the fact that it's not overlapped. You're just dead in the water doing nothing until the information from the other GPUs arrives, and then you can proceed. So there is this wrinkle with LLMs. And so now they're going to talk about something they say here. The naming convention is not very clear. And so they're going to use a particular nomenclature in this article, but just know that in other papers and whatnot, it's not. But in the sequence dimension, in terms of the number of tokens, there's different ways that you can split things. And it turns out that real LLMs don't just have MLPs and attention layers. They have normalization layers, and they have dropout. Dropout, depending on how it's implemented, might be easy if it's dumb dropout. If it's smart dropout, then it needs information. Layer norm specifically does a calculation, right, across. So I was saying if your token is embedded as 8,000 floats, layer norm needs to see all 8,000 floats in order to do the normalization, okay, in order to calculate the norm. And so for this reason, it creates a step that is not easily tensor parallelized. Okay, it just doesn't play nice with any notion of tensor parallelism, and there's really no way to slice a layer norm to get it to play nice. So what you can do instead is if you're doing an LLM that has a sequence length of 4,000 and you are doing tensor parallelism up to level 8, the MLP and the attention, you do those as we've described with tensor parallelism. And then it requires a little bit of communication. But when you get to the layer norm, what you do is you say, GPU 1, why don't you do layer norm on the first 500 tokens? And GPU 2, you do the next 500, and so on and so on and so on. And so between the 8 of them, they'll calculate all 4,000 token positions. And each one will not be using tensor parallelism. They'll just be using the full data dimension for everything. But they're just going to split up your sequence length that way. And so that's why they call this sequence parallelism, although that's not necessarily the standard name. Not everybody calls it sequence parallelism, and some people use sequence parallelism to talk about something else. But aside from the naming idea, so they have this diagram here where they said if you did just vanilla tensor parallelism, you would split it 8 ways when you do this stuff, and then when you got a dropout in a layer norm, you would actually have no tensor parallelism. This part would get no speed up, and so you can imagine, gosh, if you would hate to lose that 8-way speed up. And so what they say is no, instead, with a little bit of communication, what you can do is you can split up again, right? I said first 500 tokens this way, all the data to me, and so on and so forth. And then they go further to say there's this little bit, and I did not actually sit down with scratch paper to check it out, but it turns out that if you did not do if you didn't do anything special here for the dropout in the layer norm, you need to communicate all of this stuff in order to piece together all of your tensors that were split along the model dimension. And when you do this special sequence thing, it turns out that it requires no more communication than you would have otherwise. So the great thing is that you can add this, whatever it is, blue-green sequence parallelism happening on these steps at no relative communication cost to just doing the dumb thing where you do tensor parallelism, nothing. Tensor parallelism, nothing. And so now the actual implementation for this is even more complicated because, right, you need to tell it to split certain weight matrices by rows, certain weight matrices by columns, certain weight matrices by attention head, and do certain communication. And then at this point, you're like, oh, and now pass all this stuff from the first 500 tokens to this GPU, but the next 500 tokens to that GPU, and da 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 da. And so there's this like scatter, gather pattern, whatever. Intellectually, it makes sense to me, but like writing the code, it's kind of, and anytime anything changes, your sequence length changes, your whatever model dimension changes, all of this has to get recalculated. So unfortunately, there's no PyTorch use tensor parallelism on my LLM equals true. Not yet, not today. All right, so that's tensor parallelism, and in this article they really refer to it as tensor parallelism with the sort of obvious sequence parallelism that we're going to throw in there. And the great thing about tensor parallelism is it dramatically reduces your memory need. The bad news is we saw that it's complicated to code, and it also requires a fairly expensive communication that cannot be overlapped. All right, any questions about our second parallelism, tensor parallelism? All right, let's see here. Yeah, so here's our throughput with the two of them combined. And once again, we see going from 8 to 16 is where there's the biggest. I think these numbers changed a little bit, but the main thing is that there's this massive 40% drop from 8 to 16, not cumulative, but an additional 40% inefficiency when you go from 8 to 16. That's on their rig, because their rig had 8 H100 nodes with like the NVLink, whatever, and then they had whatever other communication between nodes, which is, fast, but it's just not nearly as fast as the communication within the node. Okay, I think the context parallelism is relatively um, not nearly as complicated as the first two. So let me see how fast we can cover this with the time remaining. Um, so again, we have the different dimensions. Data parallelism is splitting it across the batch. Tensor parallelism is splitting it nominally across the model, the data dimension. Context parallelism is going to be splitting it along the sequence length. All right. So if you are training on a length 4000, um, uh, and we're starting with just like one GPU, like theoretically, there's a lot you could do where you just say, well, why don't I send the first 1,000 tokens to GPU one, and the next 1,000 to GPU two, and third and fourth. They do share weights, so every time there's an optimizer step, there's going to need to be communication in order to keep the weights in sync across GPUs. But it's a pretty intuitive thing in terms of how you would slice it that would have fairly minimal communication. And let me see if they say anything else. Yeah, so they basically say the core idea of what they're naming context parallelism, that's not necessarily a standard name, is to do the same idea as the sequence parallelism approach, but we're not just going to do it for the layer norms. We're also going to do it based on the attention and the MLP parts where tensor parallelism already works. So, uh, ah, so now they say there's one important exception, which is that when you do attention attends to every other token position. So context parallelism works really well for the MLP portions, but it doesn't work so great for the attention blocks because they need to see every other one. And so trying to remember, yeah. So they say naively, if you did this, it's a whole lot of communication back and forth. But what people have done in order to do this is they do something called ring attention. And there's a nice little animation here, which I think tends to explain it all, where basically if GPU one starts with keys and value one, all right, eventually what it's going to do is it's going to pass it to two, so two can use it. Two is going to pass it to three, so three can use it. Three is going to pass it to four, and then you're done. So you only need n minus one communications. You don't need n. And then whatever started on GPU four, let's say key and value four, it's going to get passed one and one hop, whatever. So rather than doing a whole bunch of communications all at once to say, in this case, every GPU send your keys and values to three other GPUs. They do it serially, where they only do one at a time. And I believe with asynchronous communication, what you can do is you can overlap some of this communication with the compute. So as soon as GPU 2 gets key 1 and value 1 from the first GPU, it can immediately start sending the message to GPU 3, and meanwhile it's going to go and do its actual calculations with the keys and values. Okay, and so therefore, if this communication were serial and the GPUs were doing nothing, that would probably be bad. You'd be better off doing all the communications simultaneously. But the nice thing about this is that you're overlapping compute and communication, which is always the goal. So I think what they call in this article, they're hiding the communication because it's happening while while computations are happening. One thing they note is that when you're doing a GPT style LLM, there's a causal attention mask. And so if you naively say, I'm just going to split things between the GPUs in order by tokens, and so GPU 1 gets the first tokens and GPU 4 gets the last tokens, GPU 1 actually has to do a lot less work than GPU 4. And so they have this thing where they say, we'll give GPU 1 some of the easiest ones and some of the hardest ones. And by sort of going from ends and meeting in the middle, then it turns out that the workload on every GPU ends up being equal, and it's perfectly balanced as long as the GPUs are equivalent speed GPUs in the first place. Yeah, hand raise.
Yeah, on that ring attention,
Yeah.
is it architecturally? I see it as a ring. Things are going around from node to node, kind of a point to point. Hardware-wise, is this still a not a kind of a one to any, more of a bus type of thing or a switch?
Yeah, I think generally speaking, the way it's architected, uh, 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 it never knows who's going to want to communicate with whom. And so I think you're going through switch-like devices that
Okay.
could communicate in any direction. Um, but I think the key thing is that the ring pattern is a simple pattern and a pattern that allows you to overlap communication with computation.
Hmm. Okay.
So I think that very first pass, you may or may not be able to hide it because if you say I'm going to pass key 1 to the next GPU, but I still haven't even done my computation with it yet, then you do your computation while you're waiting for your first message.
Yeah.
And then clearly the next n-2 messages, they should be able to be hidden while you're doing computation on the data you got from the last message. And here it's showing like one key and value, but in reality, it'll be a chunk of them, right? So if you have 4 GPUs and you have sequence 4,000, then you're exchanging 1,000 of them at a time.
Yep. Okay.
So other than the zigzag, yeah, here's where they show overlapping the communication. And in this diagram, the communication lasts a little bit long than the calculation, so it's not fully hidden. But it's better than saying, let me send my keys and values to every other GPU and having this big giant dead time. So I think it really just depends on how fast your communication is and how fast your matrix multiply cores are, so whether or not this gets sort of fully hidden.
So is that
But it's
implying is that implying like a broadcast is more expensive than a point to point? It looks like.
I think it is, but also this is n-1 times as much communication, right? So with ring attention, if I have 16-way split, I'm sending my keys and values to one GPU. Sorry, with ring attention, each GPU is sending it to one other GPU. In this scheme, each GPU is sending the same amount of information to 15 GPUs simultaneously.
Yeah,
So
that's why I was
you're
wondering if a broadcast, often a broadcast is like you can broadcast it to 8 nodes as fast as you can send to one node, point to point to one node.
that's,
That's
that's
why
a
I did
decent point. Yeah. So I don't know.
it. Yeah.
I don't know. Um, uh, so again, all of these things in terms of like what's going to work best for you. At the end of the article, they say, we can tell you like what was the fastest way
Mhm.
of using these different things, how much data parallelism. In some cases, they would say none, right? I didn't use any, but how much data parallelism, how much tensor, how much context parallelism, uh, and they say this is what was optimal on our system, which involved training this version of Llama, with this H100 GPU in eight GPU nodes, blah 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 blah, right? But they said what here's the instructions for basically how you would benchmark certain things and decide what you would do for your particular use case, right? So that so they do give you examples of what the best recipes are, but they're saying, well, you're not necessarily going to use this rote if your model is bigger, smaller, has different kinds of things than our
Yeah.
model.
Yeah.
All right. Let me just check the chat real quick.
Yeah, I was just going to respond to that. It seems like it is still the same order. My one thought there might be that switches might be able to handle, in an 8-port switch, you might be able to do 4 point-to-point communications at the same speed that you can do 1 broadcast communication.
Yeah, maybe. And if that's the case, then maybe if this pink is the size of the green, then maybe you would be better off just getting it over with.
Yeah.
The other thing that happens, though, I will say, is this reduces this not only in terms of speed, but this dramatically reduces how much memory you need
Mm.
uh, uh, um, per GPU because you're storing you're sending all of them to everyone. Everybody needs to store all of them.
Yeah.
And when you do this, I think you need 2x memory because you need the current one and you need a place where you're accumulating
Mhm.
things. Maybe you need a little bit more. But so if I remember right, the first paper I saw that talked about ring attention, it wasn't really about this like super fast GPU configuration. It was really like even if you had
Mm.
terrible like 8 completely standalone computers with 1 GPU each, and the communication was really slow, right? You could use ring attention to do context length 1 million, which you just otherwise absolutely couldn't do because you would need 1 million keys and values on your GPU simultaneously.
Mhm.
So I think that's you're right, Roger. It's probably not the communication. I probably was misunderstanding. It's probably more the memory savings for dramatically large context length. For
Gotcha.
4,000, I don't think people bother with
Yeah. Yeah.
this.
Yeah. That makes sense.
Yeah, okay. And so here they say in the bullets, right? So you communicate in a ring pattern, and each GPU only needs to store 1 additional chunk temporarily instead of storing all of them simultaneously.
Yep.
This computation may not matter depending on your switch design, whether it can do, a super fast broadcast or not. All right. I don't know. Maybe let me see if I can just squeeze. Probably don't quite have time. But so the other parallelism is pipeline parallelism. You could think of it as layer parallelism. But since LLMs tend to be like 24, 30, 48, 60 virtually identical layers, a very intuitive way you can slice things is you can say, okay, I've got 24 layers. I've got 8 GPUs. I'll put 3 layers on each GPU, and there's going to be fairly minimal communication because we're just right passing, between layers in the forward pass the data, and in the backward pass a single activation. So I think that this is a relatively efficient mechanism, uh, and you can see here. Well, I don't know if you can quite tell. In terms of the the memory reduction. Oh, I see, I see. So we didn't talk about it this week. I believe we mentioned it last week. There's a thing you can do with activation recomputation. Okay. So instead of using up memory to store your activations, what you can do is you can you can throw some of them away and recompute them during the backwards pass. And there was I think a number they quoted where it was like you could recompute 70% of the activations at only a 3% compute overhead in a standard LLM. If you're being pretty clever. If you just do it by saving at between each layer, then the compute penalty is more than that. So what this diagram is saying is if you did recomputation, you only have one layer's activations at a time, or
Oh, I see.
or I'm not saying that quite right. But so basically, by splitting the layers um, amongst the different GPUs, you're not actually saving on the orange. You'll see these oranges are the same size either way. Now this um, but because you're splitting the layers 8 ways, you have 1/8 as many parameters, 1/8 as many optimizer states, 1/8 as many. If you were not doing activation recomputation, then you would also get an 8-way reduction in your activations. So, assuming if you're sort of desperate, you're probably going to go to activation recomputation also. And so then the savings for pipeline parallelism are not, as dramatic because recomputation you can kind of do as like a one-line turn on activation recomputation in PyTorch, and this you cannot. You have to actually more manually split your layers across the GPUs.
Can you help me? I'm not understanding quite that. Why is it that paragraph right under the chart describes that they're different? Because you still need to process a full batch of data. Got it, with different layers. So
What is it
each,
saying is different in this paragraph here?
well, I'm not quite understanding it. Make sure I understand what pipeline parallel means. Instead of like all my layers being on one GPU, I'm basically splitting it so different GPUs have some subset of the layers, right?
Mm-hmm.
And
Yes.
so what I'm not understanding then is why the activations don't get distributed over those end
No,
GPUs.
they would if you're doing vanilla forward pass, vanilla backward pass. But if you do activation recomputation, then you have a much smaller amount that you're saving, which is just the activations between each layer. And
Okay.
then when it comes time to the backward pass, you recalculate the forward pass for that layer, all the attention, all the MLPs. You have to redo all those calculations all over again. And so you have all the intermediate activations for one layer that you need in memory. Okay. So
Oh,
this orange box
this is
should
the
be
sorry, go ahead.
this orange box should be slightly smaller than this one because you have, let's say, 3 layers worth of intermediate things and one full inside the layer activation at a time. Whereas this one, you've got 24 in between layer activations plus the full within one layer set of
Okay,
activations,
I see.
right? And I think it's because, right, we have activations that are like n squared, right? So if our data is 8,000, then we just need to store 8,000 things between layers. But there's places where we have stuff that's like, 8,000 squared or whatever. I don't know. I don't know if I'm getting that right, but that's why you can hardly tell the difference between, 24 in between plus the full layer's worth or sorry, 24 here and only say 3 here.
Would it be 3 or would you just expand one at a time?
Yeah, you expand one, that's the majority of this, but you
Yeah,
also do have to keep something
yeah,
from
in
in between
between.
the other
Yeah,
layers. And now you only have 3 of them you need to keep, whereas here you have 24 of them you need to keep, let's
gotcha.
say.
Okay.
Right.
So if
So
you
there
weren't
is
applying
some
that,
savings, but it's kind of small
if you
comparison.
weren't combining it with that technique, then the activations would be much larger.
Yes, yes. So
Gotcha.
without activation recomputation, this orange would be approximately 24 times bigger,
Yeah, okay.
and this would be only 3 times bigger, and it would be a huge savings.
Yep. Gotcha.
Yep. Um, so the other thing though about pipeline parallelism is this all sounds great intuitively. Let's look at actually calculating things And so an intuitive thing you might do with 4 GPUs with a 16-layer model is I calculate the first 4 layers on my first GPU, and I pass the results from between layers 4 and 5 to the next GPU. And it does 5 through 8, and it passes the next GPU, and so on and so forth. And then when it's done, we start our backward pass. And so it does the back propagation on 16, 15, 14, 13. And once it gets the gradients that come out there, it passes it to the next one. And so if you look at it, you have this V shape, okay? And this takes exactly as long as if you did it on one GPU. There is zero speed up. Now you have reduced your memory requirement, so there is some benefit, but this is pretty horrible use of your GPUs. So right, so this is basically I split my memory, but I only have one GPU active at a time ever. Ugh. So is there something better we can do? And this is where, yes, what we can do is, let's say we're fortunate enough that our batch size is 8. So we're doing 8 different prompts at a time. Then what we can do is we can say, well, really the forward pass is not uh, is not just one chunk. We can actually break it into eighths. Okay. And so then what we can do is after we've processed the first prompt, we can pass that to the next GPU. And then while that's happening, we can process the second prompt and so on and so forth. Okay. So now typically we talk about mini batch stochastic gradient descent, mini batch SGD. So they call these micro batches because within your mini batch, you're further slicing it so that you can split up the communication and the communication. And so this helps. And then as we continue to read through the article, we're going to see there's more complex schemes that you can use. Okay. And then the next innovation comes from the backward pass is actually performing 2 operations. Oh, sorry. This, if you have more memory, you can sort of interleave 2 different sets of layers on the GPUs, whatever. It's still not like super great. And so the big innovation comes, where's the diagram here? Yes. So when you do the backward pass, what happens is you have 2 things that you're calculating. You're calculating the partial derivatives with respect to the weights so that you can then have the optimizer do the weight updates, okay, to change parameters. But you also have a partial derivative with respect to your input, which you're going to pass on to the previous layer, okay? And it turns out that in order to communicate to the next layer, you have to calculate the partial derivative with respect to your inputs. But you do not have to calculate the partial derivative with respect to your weights. And so if you separate what they're calling here B and W, what it allows you to do is you can say, I can do the W anytime I want while I'm waiting on communication. So what would normally be idle time, I'll fill it with one of these W's. And then you get diagrams that look like this, where the B's are the light blues and the W's are the greens. And so then you can see, depending on if you're towards the beginning, device 1, you end up dropping in these W's fairly regularly because you were the first GPU and you're not really waiting on other people. But if you're the last GPU, you spent waiting a long time until you got your first input. And what you want to do is you want to immediately do your backward pass as soon as possible in order to send the gradients back towards the first GPU, so the first GPU is not sitting idle waiting. And so that's why you'll see the last GPU does all of its back propagation steps and it backloads the weight updates till the very end. And so this general pattern you will see is that the last GPU always has a bunch of the W's that it does very late. But the first GPU, they're happy. They actually are going to aggressively do the W's as soon as possible so that they can fill time when they're waiting for the last GPU and everybody else to back propagate all the way back to them. So that's the general nature. And so there's the zero bubble paper or papers, and then eventually we had DeepSeek, where they did this technique where I believe they were GPU rich, so they could afford to use only half the memory of the GPU at a time. And so they used half for, I can't remember, like early layers, half for late layers, and interleaved those so that what I was talking about here, about this GPU being just the earliest one, now basically half of it is early and half of it is late. And so this one, instead of being just the last GPU, actually half of it is the last GPU, but half of it is the first GPU. And so then instead of seeing here where you just have a straight staircase coming from the top, now you see a stair coming from the top, a stair from the bottom, they're meeting in the middle, and then doing this. And so if you can figure out on my GPU for this exact LLM, how long does the forward take? How long does the B take? How long does the W take? You can try to manually figure out a pattern that has as few of these little white bubbles as possible. And if you guys remember from the DeepSeek paper when we talked about it, it turned out that I think they had a bunch, I don't remember which way they had to tune it, but basically they had a bunch of bubbles because they were waiting for communication. The communication was too slow compared to the computation. And so this is where they actually went in and did low-level optimization to say that the what the heck are those things called? I'm blanking now. But the little compute engines on the GPU, NVIDIA gave you X much compute for communication and X much compute for matrix multiplies. And they needed to change that allocation. They needed to change the split between streaming multiprocessors, right? They needed to change the number of SMs doing communication versus the number of SMs doing matrix multiply in order to balance it so that for this scheme here, they got it to where it was almost exactly equal and had as few bubbles, zero bubbles as possible. So this stuff can work, and the Llama 3 team got it to work. The DeepSeek people got it to work, but you can see why it'd be a heck of a lot easier to just turn on gradient accumulation if you just needed a little bit of a whatever. And that's why back in that other diagram, they were saying, and we'll just assume that you were using gradient accumulation if this was a problem. We're just assuming you're using gradient accumulation because that's one line of PyTorch code to turn it on versus having a whole bunch of specialized engineers, doing all of these complex timing calculations of your GPU and having to write low-level code for your GPU in order to get it to execute this fancy pattern. But yes, you'll read about this pipeline parallelism, and for me, it's like very intuitive. Oh, it's really easy to split your bottle by layers. The problem is that they're just going to be sitting around, and you have to do this fancy stuff to prevent them from being sitting around. All right, we're a little over time.
Hey, Ted, quickly, then that would change, right, if you change the hardware configuration in any way?
Absolutely. Or you change your model in any way.
Any substantial way, yeah. Okay.
So if you look at all the work they did for training DeepSeek V3, their 671 billion parameter model, if they have a DeepSeek V3.1,
back to the drawing board.
Back to the drawing board. You might need a completely different pattern, and you might need to change the number of streaming multiprocessors doing communication by a slight amount, and you might need to all these things. So you can see those other parallelisms are a lot easier to tune
Yeah.
than this.
And it seems like there'd be dependencies too on, what happens at what point in the stream might affect something downstream too.
Yeah, and then what's going to happen is we're going to mix in expert parallelism, and that's a little bit harder to
Oh.
time than vanilla. And then what if you wanted to do this, but you had 20,000 whatever the heck they were H800
Hmm.
GPUs and another 10,000 that were slower.
Yeah. Yeah. Like the DeepSeek problem, right? They had a mix. And
They had
so
a mix.
it was heterogeneous. So it was a
Yes.
problem there.
Yeah. So then you got to kind of think about, oh, okay, where do I put the slower ones? And
Mhm.
maybe you can just do something where you're like, okay, the faster ones get 5 layers each, and the slower ones get 3 layers each. But you can just imagine that you really, really need to spend a whole bunch of time tuning it. Um, and then as soon as anything changes slightly, you're
You're,
just,
it's back to the drawing board again and
yeah,
retune,
I mean,
right?
I
Although
assume once you've done it once, you get good at it and you know how to do it quickly, but you are doing it all over again.
I think that the zero bubble people actually had an algorithm to compute it.
Mm,
Hmm.
So
very cool.
given this performance, this is how you should lay it out.
Very, very cool. That's yeah. And
I
and
think,
that's both your matrix multiply performance and your communication
yeah,
performance.
all of it. Yeah.
Yeah.
Yeah, because you have
Because
those two
fortunately,
ratios.
because fortunately the kind of the operational time, the number of flops is constant, so it's predictable. So you can schedule it once you know.
Yep.
So
Cool. All right. So I think we'll stop here. We've actually gone a long way. We've done 4 of the 5 degrees of parallelism. The last one, expert parallelism, won't take that long. But if we have time next week, we can talk about some of the other things in the article that go past um, just the different degrees of parallelism. They talk a little bit about the architecture of the GPU and flash attention and
pretty
different
cool.
size, right? Do you have 32-bit float, 16? Do you have an 8 like DeepSeek tried to use or did use, sorry, and some of these other details. So I think we can throw some of those in and then some high level questions. And, again, for me, I'm not planning on training a giant LLM anytime soon. And I also am not holding my breath for the day when I have some large number of GPUs at my disposal that I need to uh, implement these strategies. But I do find it very helpful to uh, understand this context when we're reading about, hey, we just trained this big rock, we trained this new llama, we trained this new DeepSeek, right? And what is this the stuff they use? And some of this does then carry over to understanding. This is training, which is more complex because it has the back propagation, but some of this does help to understand inference and really like, you know, for me, I feel like I more deeply understand the way LLMs and GPUs work just by going through this, even though I'm not actually expecting to have 20,000 GPUs that I need to figure out the 5 different parallelism techniques and how to split them.
Cool. Thank you, Ted.
All right, cool. Any questions? Crowd's been pretty quiet. Either like this article did a really great job explaining things and everything just made sense, or I don't know.
Or maybe you just did such a wonderful job explaining it.
I mean, I
Actually,
definitely didn't cover everything. I glossed over some things. And then I can't remember. Uh, there's one week, Jerry, that I owe you the recording so that you can get it posted to YouTube. I don't remember if that was last week or the week before. But
Jerry's probably
you're on
he's
mute,
on mute.
Jerry. But if people are waiting for last week's and that's the one, then it's because I owe getting that to Jerry.
yeah, it is last week, Ted. I'm sorry.
Okay.
They're on me,
Yes.
but-
Yes. So I saw in the chat somebody asked about last week, and so yes.
Yeah, we'll get
Oh,
that and we'll get it out. fairly quickly up onto YouTube, and then we'll get this one right behind it. So,
So
okay, I'm going to stop the recording for this one, though.